We might actually finish up with some time left over. If that happens, we'll move on into chapter 5, but that won't be on the exam. It'll just be chapters 3 and 4. Those are two pretty big chapters with 2D motion and Newton's laws. We left off with Newton's third law. Remember, Newton's third law says that if you have a force, you have an equal and opposite force, a force that's equal in magnitude but opposite in direction. That's true for contact forces. So, for example, if we have, an object on a table that's in contact with the surface of the table, there are a couple of forces acting on this. We have the force weight of the object, and then we also have a separate force. We'll talk about this in just a minute, but this is called the normal force. And this arises or is described by Newton's third law. So my normal force will have a magnitude that's equal to the weight. In this case, for this particular scenario, that's equal and opposite. So the normal force is equal in magnitude, but opposite in direction. Right, yeah, so the normal force, yeah, so it'll stop it from going to the center of the earth. And so, like, you feel a normal force right now, that's the force pushing back up on you from the chair. If you stand on the surface of the earth, the normal force is just the earth pushing back on you. You can also feel normal forces. It doesn't have to be gravity. If I just push on an object, then that object pushes back. That's called the normal force. But we also see this with field forces. We'll have a chapter on this later at the end of the semester on gravitation, but if we have two objects of certain mass, M1 and M2, right, they exert forces on one another because objects of mass, because of the gravitational force, exert forces on one another. So we'll talk about this later, but these forces are equal in magnitude but opposite in direction. So mass 2 exerts a force on mass 1. I'll call this the force on mass 1 due to mass 2. And this is the force on mass 2 due to mass 1. So there's this property of mass, we don't fully understand, but that it's attracted to other properties of mass. And that's where we get the acceleration due to gravity, because we have a certain mass, and the Earth has a certain mass, and so they're attracted to one another. But we'll talk about more about that later in the semester. This Newton's third law applies to both contact forces and to field forces. So this is contact, and then these are field forces. Remember, field forces do not require contact between two surfaces. And the result of this law is, I don't know if you think about it, it's kind of fascinating, but the result is that no isolated force exists. That anytime you have one force, you have another force that's equal and opposite in magnitude. So you cannot have a single isolated force. Okay, so what about the force due to gravity exerted on you by the Earth? Is that an isolated force? Like, for example, let's say that I'm not dealing with contact forces. This is the northern hemisphere, and let's say that I am suspended over the Earth, and I have a certain force. Say I have a weight of about how many newtons? First, about 700, yeah, so about 700 newtons. Is that an isolated force? Is that an isolated force? That force of 700 newtons that's pulling down on me. No, why not? Why is it taking? Why is it not an isolated force? Because I'm pulling back up on the Earth. So the Earth is pulling down on me, and similarly, I'm pulling up on the Earth with a force of 700 newtons. But because the Earth is so massive, it causes such a tiny acceleration that it's imperceptible. Right? That 700 newtons on this one solar mass planet doesn't really do anything. Let's see. So as I said, contact forces also obey Newton's third law, and the result of this is called the normal force. So as I said before, we have this sort of block on a table. If I want to find the normal force, I can apply Newton's second law as we've been doing. I've already done this. Let me just show you sort of rigorously from that the normal force is equal to the weight. So this is my normal force, this is my weight, and so I can show then that by Newton's second law, the sum of the forces equals ma. In this instance, we're doing the y component of the forces. So that's going to be the normal force minus the weight equals ma. But if we say that the acceleration is 0, then we can say that the normal force is equal to the weight. So if I have stationary objects that are not accelerating, and they're sitting on a horizontal surface like this, our normal force will always equal our weight. Well, no, that's not entirely true. There is a way that I could increase the normal force in this scenario. How could I increase the normal force or decrease the normal force? What would I do? Huh? Yeah, so if I apply another force to it, so if I apply a force here, let's just call that F, then it would change this calculation. I would have Fn minus Fw minus F is equal to 0, and then Fn would equal to Fn plus F. So you can increase the normal force, and that'll be important later when we talk about friction, because the frictional force is related to the normal force. You probably know this intuitively, right? Like if I have an object that's sitting on a table, there's a certain amount of friction that holds it down. Well, if I push down on that object and I try moving it, it's more difficult to move because I've increased the normal force by pushing on it, and then that in turn has increased the frictional force. So we'll talk about that reliance upon the frictional force to the normal force. If I increase the normal force, I increase the frictional force. Okay. Let's see. So the normal force isn't necessarily equal to the weight of the object. This can come about either because the object is accelerating, let me show you that. Let's say that I have an object, let's forget about this, I'm going to do some other scenario. Let's say I have an object that's, say, in an elevator, and it has a mass of, say, 10 kilograms, and this thing is accelerating downward at 2 meters per second squared. We had a similar problem, except it was, being suspended by a rope, and I want to know what is the normal force in this case. First, I'll draw my vectors. I have the normal force acting up and the weight acting down, and then they're already on the y-axis, so I'm just going to apply my Newton's second law. Sum of the forces equals ma. That's Fn minus Fw equals ma. And then solving for Fn, it's equal to Fw plus ma. Alright, and then Fw is 10 kilograms. That's 10 meters per second squared. Plus 10 kilograms times what? What's my acceleration here? -2, right? So -2 meters per second squared. And then so I can find that the normal force is equal to 100 minus 20, that's 80 newtons. Alright, so if I have an object that's accelerating downward, the normal force decreases. You experience this in an elevator, right? That's why when you go into like a really fast elevator, when it's going downward, you sort of feel that lurch. And the reason you feel that lurch is because physically the normal force is decreasing. So you're feeling a different normal force than you would normally. Likewise, when it goes up really fast, what happens to your normal force? Does it increase, decrease, or is it equal to your weight? If you accelerate upward in an elevator, it decreases. No, it decreases here. This is when we're going down. What happens if you're going up in an elevator? It's going to increase, right? Because if we look at this, if we're traveling upward, this equation would change because the 2 would become positive. Say if we were accelerating upward at 2 meters per second squared, then our normal force would actually increase. See, I'll try that if you like. The elevator here doesn't really do it so well, but if you have a really fast elevator, I'm not sure there is a fast elevator in Thibodeau, but I don't know, maybe at home or New Orleans or whatever. But if you go up really fast, you sort of feel this pull downward, and it's because your normal force is increases more than your weight. Okay, normal force is always normal to the surface. What does normal mean, though? That's not what I was going to put there, but what does normal mean? Perpendicular, right? So normal is just a fancy word for perpendicular. It doesn't mean usual or ordinary. It means perpendicular. So the normal force is always perpendicular, or also another word we can say it's orthogonal to the surface, but normal or perpendicular are the same things. This will become important when we do inclined planes, and we'll do one of these next. But so if I have an object on an inclined plane, then my normal force here is not up, but my normal force is perpendicular to the surface. So if I draw an angle here, it's going to be 90 degrees to the surface. Perpendicular means. So normal means perpendicular. It's just a mathematical term to mean perpendicular. All right, let's work through an inclined plane problem. Very likely to have an inclined plane on your test. You could see a different type of problem, but it'll be similar to an inclined plane. We'll work through some different examples, but very likely to have an inclined plane. And there are some examples in your homework and in the old exams. Let's say that we have an object like this, and I want to know, well, in this case, the normal force is some value more or less than the weight, or equal to the weight. How is the normal force compared to the weight in this case? Is it equal to, less than, or more than the weight of the object? It's going to be less than, right? Because in this case, the normal force is just a particular component of the weight. If I break my weight into its two components, I have FWY right here, and then I have FWX right here. And so I look at these in the y direction. I say the sum of the forces in the y direction equals MAY. AY is equal to 0. So then I can say that Fn minus FWY is equal to 0, or Fn is equal to the y component of the weight in this case. When there are no other forces acting upon it in the y direction, the normal force is just equal to the y component of the weight. Let's do a simple problem. And this is a little simpler than what you'll have on your test, but it's good preparation for that. This was actually from an MCAT book. I have this mass on this box and this figure up here. And let's say that the mass of the box is 10 kilograms. What force must be applied so the box is stationary? So I'm just going to redraw this. And we want to follow those steps. Let me just remind you of the steps. You want to label and identify the forces. You should already have these steps in your notes somewhere, but it helps to just sort of keep these in mind. Because you know each problem is going to be a little bit different, but if you follow these steps, you'll still apply all these steps. So label and identify the forces, draw the coordinate system, and for your inclined plane, that coordinate system will most of the time be the same. The third thing was to resolve into our x and y components. In the course of that, you'll need to identify the appropriate angles for finding the x and y components. And then the fourth thing is applying Newton's second law. And you'll do that on all axes. Once you apply Newton's second law, you'll just get a system of equations, and then from there, it's just, well, what am I looking for, and what do I know? And so it's solving that system of equations. Later today or Wednesday, we'll actually look at solving systems of equations by matrices, like inverting matrices. Have you all ever done that? In your algebra, I think you do it, right? Oh, you're doing Calc 3. Okay, we'll do that here. And actually, that'll be for extra credit on your exam. So you don't have to know how to do it because that's not really the purview of this course. But it's a pretty simple way to solve, well, I don't know that it's simple way to solve systems of equations, but it's a very useful way to solve systems of equations. So we'll do that for this, and you can do that for extra credit on the exam. Okay, so let's first just draw the figure. I had an inclined plane. I have a block that's sitting on it. And I know that I have several forces. What are they?
Force operating the normal force.
Right, so I have the weight of the object, Fw, and then my normal force, which is perpendicular to the surface. And then I have a third force. What is that? Because as this object is going to be sliding down the inclined plane. Right, there's nothing here that's holding it in place. It's just going to slide down the inclined plane. But I know that it's stationary. The problem tells me it's stationary. So where's the other force? Friction. Okay, well, it's not friction yet. We're not talking about friction. But how would you draw the force on this figure? It tells you in the problem, right? That there's a force directed up the inclined plane. Okay, yeah. So that's our third force, excuse me, is a force that's directed up the inclined plane. And that will be friction in the future, but right now we're just saying it's some generic force. All right. Now we want to draw our coordinate system. So on an inclined plane, for several reasons, we'll draw our coordinate system so that the x-axis falls along the plane of the incline. We do that for a couple reasons. One, we already have forces that are along those axes. So like the normal force is always on the y-axis. And so it's a nice way to draw it so that we already get some forces on the axis. And then also the frictional force will always be on one of those axes. Another reason is for our acceleration. In this case, this thing's not accelerating at all. But what if it was accelerating up or down the inclined plane? What would be the result if we didn't draw a rotated coordinate system? That is, instead of drawing it like this, we drew our x-axis like this and our y-axis like this. How would the acceleration, what would be a problem with doing that with regards to the acceleration? Of the acceleration, right, yeah. So we would have an acceleration that was neither just on the x or just on the y. It would be on the x and the y. So we have an ax and an ay, right, an x and y component of the acceleration. But in this case, if it's moving, it only has which of those components? Well, we're calling this the x-axis right here, and this the y-axis. So if it's moving, what direction? X or y? It's moving in the x direction. Okay? So we've done steps 1 and 2. Now we need to do step 3. Let's call this angle right here, and we'll always identify our inclined plane by this angle. We'll say that that angle is 30 degrees. And now let's redraw this. You don't always have to redraw it, but it's often nice to redraw it with our vectors. So here's my normal force. Here's my force along the plane. And then I have my weight, which is here. Okay. I usually define this angle for a vector. So given that inclined plane, what is that angle? What do y'all think? What is that angle? It is 60 degrees, that's right. So this angle is equal to 60. We can get that because if you look at this triangle, we have a triangle right here. All right, this angle is 30 degrees. So this angle then has to be 90 minus 30, which is equal to 60 degrees. All right, so the angle for that weight is always going to be 90 minus the angle of the incline. You really just have to draw your picture to see that, okay? There are some scenarios where we might deal with inclined planes, maybe where it's not a right triangle, but instead it's an isosceles triangle, where it's like this instead of like this, where that might be a little bit different. We might see some examples like that, but always draw a picture. It always helps me to draw a picture. Okay, so yeah.
So that's 30 unless it says otherwise?
No, I'll always tell you what the angle is. All right. It's just that we usually identify our angle by this angle, not by this angle. Right. Although we know what this angle should be, right? What should this angle be? Right, so that's 60 degrees. So Now we want to find our x and y components, and then we can apply Newton's second law. I'm going to go down to the next page. I'm going to draw my x and y components. On the exam, you might not redraw all of these, but I find it useful to draw at least one vector diagram, and then you can go from there. So there's Fn, here's F. This is going to be Fw cosine of 60, and then this is Fw sine of 60. Let's see, what was our mass of the block, did I say? Okay, so let's go ahead and write this up here. So my mass is 10 kilograms, and I want to know what is F equal to. Alright, so now I've resolved my vectors into their x and y components, and now I'm going to write Newton's second law for each of these. Remember, Newton's second law says that the sum of the forces in the x direction equals max, and the sum of the forces in the y direction equals may. We only have one body that's concerned here. Later we'll do problems where we have two bodies, and in that case we'll have a system of 4 equations. But here we only have a system of 2 equations because we only have 2 bodies. Or excuse me, one body with an x and a y component. Is that clear what I mean? Okay, so we have 2 equations. The sum of the forces in the x is going to be Fw cosine 60 minus F equals max, but our acceleration is equal to 0 in both the x and y components, so this is going to be equal to 0. So this will be equation 1, and then equation 2 will be the sum of the forces in the y, Fn minus Fw sine 60 equals 0. Only 0 because the acceleration is 0. Later we'll do some problems where the acceleration is not 0. So we'll look at a couple of variants of these problems. On a simple problem like this, we'll add in friction, which will really just be saying this force is our frictional force, and then we'll add in where we have 2 bodies instead of 1, and then we'll also add in where it's accelerating instead of not accelerating. So we'll see some variants of this, but you know, one of those will be on your test. Okay, so this one's pretty simple because I know a lot of information here. In fact, both of these equations only have one unknown. This one is not known, and the normal force is also not known, but otherwise I know everything else. So if I'm looking for F, it's just going to be Fw cosine 60. Let's see, so F that's going to be 10 kilograms times 10 meters per second squared times 0.5, which is cosine of 60, which is 100 times a half is 50 newtons. So that's the answer, is that the force up the incline has to be 50 newtons. Alright. And then if I wanted to find the normal force, I would say the normal force is equal to Fw sine of 60. Notice here the normal force is what component of the weight? The x or the y? That's the y component of the weight. So that's going to be 100 times sine of 60, which is, what, 86 newtons. Right? Let's call it 90 newtons. Alright? That's a simple problem, but it still has all the steps that we'll need. And those steps you'll follow throughout. Y'all are okay with this? This problem? As I said, the problems on your exam will be more difficult than this, but we'll do some more. This is a good base to start from. Alright, let's try this clicker question. I have here a figure on an inclined plane, and then I have a series of equations, some of which are incorrect, and there's only one correct equation. I want to know which of these is the correct equation. Which of these is correct? when you apply Newton's second law, you get a series of equations. Which of these are correct? Now you can go through because some of these have forces that are on the x-axis combined with forces on the y-axis. So you know that that can't be a correct equation because the x and y components of forces are not related.
So there's not going to be a force opposite of F?
There is a force opposite F. This force, there's a component of the weight that's opposite the force F. So we break our weight into its x and y components, and the x component of that weight is opposite F.
Okay.
Well, in this case, is it moving or not? It says, yeah, the block is accelerating up the inclined plane. That would be in the positive x direction as we draw our coordinate system. Be careful with your angles here. Notice there's some 30-degree angles and 60-degree angles. So be careful on that. About 20 more seconds or so. Stop at 320. Just guess if you don't know. 320. Alright, so you could look back at what we've already done. Oh goodness, let's see, B and C. So, you're right that D is not the right answer, because D, if these are my axes, D says that the weight is equal to the normal force, but I know in fact that the normal force is equal to the y component of the weight, right? Not just the weight. And so if I break up my weight here into FWX and FWY, it shows that D is not right. Also, A is not right for a similar reason, because the normal force, Fn, is on the y-axis, but this force F is on the x-axis. And those forces are not related to one another. Remember, we keep our x and our y separate whenever we're dealing in Newton's second law. So A is not the right answer. Let's see, let's look at B. It says that the normal force minus, that's the x component of the weight, is equal to max. So a couple of reasons that this is wrong. First of all, the normal force is on the y-axis, and it says that that is somehow related to the acceleration in the x direction. So that should have keyed you off that that was not correct. The other thing is, and the reason a lot of y'all put this probably is because you have this sine term here, but notice this is the sine of 30 degrees. And the sine of 30 degrees, FW sine 30, is actually equal to the x component of the force weight, FWX. So I'll remind you that sine of 30 is equal to cosine of 60. So this would be the same as writing FW cosine of 60. These two are equal to one another. So whenever you're finding your x and y components, you have to be careful because you're not using this angle if you're using the cosine for your x component and your sine for your y component. As I recommend you do that, it makes it a little easier. But instead we're using 90 minus this angle. So in this case, if we're finding our x component, it would be FW cosine 60. Alright, so B is not right because this is the x component of the weight, and the normal force and the acceleration are in different axes. So that leaves C as the correct answer. Most of you got, half of you. And C, we can find that our FWY is equal to FW sine of 60. That's our Y component of our weight. Remember, this angle right here is equal to 60 degrees, and so the sine of 60 times the magnitude of the weight is equal to that Y component. So C is the right answer. You with me on this, y'all? Yeah, kind of. We're gonna do it a lot, so let's do another example. Let's see. Oh, did we watch Big Buck Bunny? Okay, well, we watched a clip. This is another clip from Big Buck Bunny. Right, so in Big Buck Bunny, right, you had this big, sort of naive, innocent bunny. So I think the clip I showed you is like he set up all the spears and stuff, so he looks sort of like the bad guy, right? Did y'all think he was the bad guy? No, he's not. He's the good guy. He's been beat up by these squirrels. And so at the very end of the little movie, it shows him where he does this thing to the squirrel. Well, let me just show you the clip first. See, I don't think I have it. I'm going to pull it up on YouTube, so give me just a moment. Okay, so I'm going to redraw my little vector diagram here. I had FA, which I want to know. FW was straight down. And FT was off there. I'm going to draw my vector diagram, or my X and Y axes, and I estimated this angle to be about 45 degrees, just from looking at it. So that's the scenario that we have. We said that Ft is equal to 10 newtons, and Fw is also 10 newtons. And so I want to find now what is Fa. So first, I'll do my X and Y components of Fw. What's my X component of Fw? That's the X component of this force right here.
0.
Right, it has no X component, or it's equal to 10 newtons times the cosine of negative 90, which is 0. And then my Y component is equal to, okay, not just 10 newtons, but what? No, it's negative, right. So my Y component is negative. If you want to do this with our sine and cosines, you could say 10 newtons times the sine of negative 90 degrees, and you would find that it's negative 10. Sine of negative 90 is negative 1. And then what's Fs? Oh, that was the string. Our Ft here is the same. And that's going to be, my X component is going to be 10 cosine of 45. My Y component is going to be negative 10 sine of 45. I'm using my trig functions there. Notice if this is my,
How do you know that FT is 10
I just guessed. I just sort of estimated it. All right. So you ever flown a kite? You don't get a real strong pull on the string. It's probably just a few pounds. All right. Why is my Y component here negative? Why is my Y component negative? Okay, yeah, it's pointing down. That's right. So my Y component is pointing down. My X component is in this direction for Ft. So this is Ftx and Fty right here. So the Y component is pointing down. And then if I want to know Fw plus Fs, I just say, let's see, this is equal to, what's cosine of 45? We have 0.71. So this is equal to 7.1. And this is equal to negative 7.1. So I can find the sum of the X components is going to be 0 plus 7.1 is just 7 plus 7.1. And then this is going to be negative 10 minus 17. And then so since we had said before that the air resistance is equal to the negative of Fw plus Fs, or Ft. the tension in the string, and we just take the negative of these. So this will be negative 7.1 and positive 17. Those are the x and y components then of FA. The force due to the air resistance. And so given that, I can find the magnitude and direction. So if I sketch these in, I have negative 7.1 in this direction and positive 17 in that direction. Negative 7.1, positive 17, and then I can find the magnitude and direction of FA. And let's see, that is 18 newtons. And the angle for this is going to be the inverse tan of the y over x. That's 17 over 7, which I find to be 67 degrees above the negative x-axis. Right, so it becomes just a basic vector addition problem. Okay? You could see just a basic vector addition problem, or maybe something along in this line as well, where you just have to do basic vector addition to find an unknown force. On the test, I mean. Y'all can do vector addition for the test? Yeah. I think y'all have your midterm too, right, this week? On Thursday, is that right? In the lab? Oh, it's next week for y'all.
Some people still have it this week.
Yeah, some people do. All right, let's do some more clicker questions. I forget where we left off here. Do y'all remember? Or did we get to friction? Does anybody mark it in their book? You did mark it? Let's see where we left off. Oh, we didn't do chapter 4 at all? No? Okay, let's do these until the end. We still have about 10 minutes, 5 minutes. Okay, so book is lying at rest on a table. The book will remain there because what? Which of these? So I just have something lying on the table, it's at rest. Why does it stay there? You can think in terms of Newton's first law or Newton's second law. Either one of those would explain it. Do you have an organic test today? All right, about 10 more seconds. Let's stop at 55. $8.20 or $8.25? $8.25. Right, this class. Okay. Okay. Option A is not correct because if there's a net force according to Newton's second law, what has to happen? If there is a net force, what has to happen? No, it has to accelerate. So by Newton's second law, the sum of the forces equals ma. If there's a net force, then it has to accelerate. So option A then is not correct. Are there forces acting on the book? Okay, there's a lot of forces, right? First off, there's just the weight and then the normal force. And then there are forces sort of internal to the structure of the book, the molecular forces. And C, no, I put C, it's not moving. So the answer then is D, that there is no net force. And E is also not correct. If there is any force at all on the book, any net force at all on the book, regardless of how massive it is, it will accelerate some. It might be very, very small, but it will accelerate some. So D is the right answer. There's no net force. Hockey puck slides on ice at constant velocity. What is the net force acting on the puck? is traveling at constant velocity. I'm going to stop at 55 seconds. 55. Okay, E is right. If I have a net force of 0, that means I have 0 acceleration. Constant velocity is 0 acceleration, so those are the same. You put a book on the bus seat next to you. When the bus stops, suddenly the book slides forward off the seat. How would you explain this in terms of Newtonian ideas, not Aristotelian? Alright, I'll stop at 55, 55. Oh, we'll stop at 1 minute, 1 minute. So just 10 more seconds. Okay, let's try it again. I'm going to tell you that A is not the right answer. Most of you will put A. So A is not the correct answer. I'm going to stop at 20. Just try it again. Okay, you're just sort of spreading out among the others. I'll go to 25. 25. Just guess if you don't know. Okay, so B is the right answer. If I have this bus seat, and then I have a book lying on top of it, as the bus is traveling along, right, so this sits inside a bigger bus, the bus is traveling at a certain velocity. That means that the book is also traveling at a certain velocity. And then when the bus stops, if the book keeps traveling along, what hasn't happened? Right, yeah, so the book is continuing to travel along at constant velocity, but it's the bus that's stopping. So if the book were to stop, that would mean that a force would also act upon the book. So the answer then is B, that no net force acted upon it. What is the force that usually acts on the book if it doesn't slide off the seat? No, it's not the gravitational force that holds it on the seat. Not the weight, it's the friction, right? So usually it's the frictional force that holds it on the seat. But if that's not enough to hold it, to stop the acceleration of the book, or to stop it from accelerating, it's going to slide off. All right, you kick a smooth, flat stone on a frozen pond. The stone slides, slows down, and eventually stops. You conclude that which of these? Looks like our answers are evenly split between B, C, and E, right? Evenly split. It is one of those, but which is it? You can chat with your neighbor if you like. All right. One of these is sort of the Aristotelian view of thinking about things, the way that Aristotle presented it. Which one of those, B, C, or E, is the way that Aristotle would present it? E is the Aristotelian view, that objects have this natural state, and obviously that's not right. Okay, so E is not correct, and that's the way that Aristotle would think about it, that these objects have a natural place to be at rest. So E is not correct. Okay, I'm going to go ahead and stop. I'll stop at 148. 148. Okay, C is the right answer. Notice E is not the right answer. So I know that's sort of the way that we like to think about things, but E is not correct. So what is the force? We know that a force has to be acting upon it because it's slowing down. So it's decelerating or it's accelerating in the negative direction. So it has to have a force, and that force is the force of friction. See, I think we have time to do one more. Have a cart on a horizontal frictionless table. Once the cart has been given a push and release, what will happen to the cart? It's on a completely frictionless table. So I'm going to stop at 45. 45, this is our last one, so put your stuff away if you like. 45. Okay, D is the right answer. Absent any forces of friction or whatever, it'll continue on at the same speed forever. That's Newton's first law. All right, we'll do some more of these next time. And next time, in the next couple of class periods, we're going to do more problems that will be more like what you'll see on the test. So important that you come. They're in the notes, they're in the old test, and we'll work through some of those. You have a good day. See ya.
Question